All right, welcome. In this video, we are going to be covering sketching rational functions. So let's just start off by remembering that a rational function is just a function that it's written in some sort of fraction form. So we could see like x squared minus 4 over x squared plus 2x minus 8 or something along those lines. All right, this is a rational function. We've got a numerator and denominator with x's sometimes in both the numerator and the denominator. So the cool thing is at the end of the video, we're going to be able to sketch a function that looks similar to this. All right, so what do we need to do in order to sketch a rational function? We're going to have 4 main steps, and it doesn't necessarily matter which one of numbers 1 and 2 you do first. But we're going to follow these 4 kind of guidelines as we are sketching our rational functions. So the first one is we just want to identify any discontinuities as well as asymptotes, both vertical and horizontal asymptotes, both removable and infinite discontinuities. Okay, then we'll identify our intercepts, our x-intercepts and y-intercepts. Then we're going to use limits to describe the behavior at asymptotes and just discontinuities in general. So if we have a removable discontinuity, we still want to use a limit just to describe like what y value would that be. All right, and at the very end, we're just going to put all of that together. So really our most important step, and the one that people have the most trouble with, is probably that third step where we're using limits to describe exactly what's happening in the graph. All right, and if we can't do 3, there's no way we're going to be able to get to 4. All right, so we're going to start off with one example here. We're starting off with f of x is equal to x minus 4 over x squared minus 2x minus 8. So with these functions, we just want to start off by factoring both numerator and denominator really as much as we can. So my numerator stays as x minus 4. In the denominator, I have x minus 4 times x plus 2. So right off the bat, I see I have a factor in the numerator and the denominator. So the same factor appears in both the numerator and the denominator. Well, when we talked earlier about these kinds of functions, we could kind of cancel those out, but it's important to understand there is going to be a removable discontinuity there. So we have a removable discontinuity, or a removable I'll just stop it there, at x equals 4. Because if we were to plug in 4, we would get 0 divided by 0. That is a removable discontinuity at that value. And then we know if we plug in -2, right? -2 is definitely not in the domain of this function. Well, what kind of discontinuity occurs there? That's going to be an infinite discontinuity, and that's the same thing as a vertical asymptote. So we have an infinite discontinuity at x equals -2. Again, that's the same thing as our vertical asymptote. Now, the only other thing that we are looking for is our horizontal asymptote. It's important to remember our horizontal asymptote is just what's happening as x approaches positive or negative infinity. Is there some value that our graph is going to approach? Well, we can approximate f of x by saying, well, if you have infinity or negative infinity minus 4, does that minus 4 really matter? No. So as x goes to positive or negative infinity, the numerator can really just be approximated as x. And my denominator, well, infinity squared, or like 1 billion squared, is a lot greater than -2 times 1 billion. So again, all we care about from the denominator is just that term with the highest exponent. So we have x over x squared that we know is the same exact thing as 1 over x. Now you might be asking, well, how does this help me? Well, again, remember that we're kind of imagining what happens as x goes to positive or negative infinity. Well, plug in infinity. If you do 1 divided by a billion, you get 0.000000001. All right, it's really going to approach 0. So as x goes to positive or negative infinity, we're getting closer and closer to 0. So that is our horizontal asymptote, is y equals 0. Now, it is important that we say the horizontal asymptote is always a y equals if it exists. And then our vertical asymptote is an x equals if it exists, okay? You can't just say vertical asymptote equals -2. That doesn't really mean anything. The vertical asymptote is the line with equation x equals -2. All right, so working with the same problem, now our goal is to find the intercepts. Well, how do I find these intercepts? My y-intercept, that is just whenever my x value is equal to 0. So when my x value equals 0, which means I'm just going to plug in 0 for x. Plug in 0 for x. In the numerator, I get -4. In the denominator, I get 0 minus 0 minus 8 is -8. So I get a 1/2. All right, that is my y-intercept for this problem, is 1/2. Now, what about for my x-intercept? All right, my x-intercept occurs whenever the function is equal to 0. So, well, let's think. This is a fraction. Right? So my question is, for what x values is f of x equal to 0? So I'm looking for an x equals, what is x going to equal? Well, think of fractions. When's a fraction equal to 0? Whenever the numerator is equal to 0. So all you really need to do is take the numerator and set it equal to 0. So I say x minus 4 equals 0. I get x equals 4. Well, is this my x-intercept? Let's think back. What exactly is occurring at x equals 4? At x equals 4, I have a removable discontinuity on the graph. So that point doesn't actually exist. If I were to plug in 4 up here, I would get 0 divided by 0. That's indeterminate. We don't actually know if that's equal to 0, 1, infinity. We have no idea what that's equal to. So that's not an x-intercept because a removable discontinuity occurs there. So we're not going to have any x-intercept here, no x-intercept. So at no point should our graph be crossing the x-axis. All right, now using limits to describe the behavior. So we want to describe the behavior at any asymptotes. So if we think back to when we originally did limits, we want to start off by saying, all right, well, let's start off with my infinite discontinuities. What's going to occur at my infinite discontinuity? Well, I can't just say what's the limit as x approaches -2, because if we remember, think about that vertical asymptote, right? Is it always going to go to the same value on each side? No, I mean, sometimes it does, but not all the time, and we can't just assume. So we need to specify what happens as we approach that infinite discontinuity from the left, and what happens as we approach that infinite discontinuity at x equals -2 from the right. Okay, and then, okay, for the removable discontinuity that we have at x equals 4, well, think about a removable discontinuity. It's just that hole in the graph. It doesn't matter if we come from the left or the right, so we don't need to specify it here, because from the left and from the right, we're going to be approaching that y value of the hole. All right, so we don't even need to specify from the left or the right. Then the only other limits we want is just our end behavior limits. So what happens as x goes to positive infinity? What happens as x goes to negative infinity? All right, so let's start off with this -2 from the left. Okay, so what happens as we approach -2 from the left? Well, we want to plug in a number that's really close to -2. We want to get as close to -2 as we possibly can. So we're not going to plug in like -2.0000001, right? -2.1 or -2.01 will suffice, right? That's 0.01 to the left of -2. That's pretty close. All right, that's relatively close, and for sake of these problems, that is close enough. So I'm going to plug in -2.01, and all I care about in this case is what is going to be the sign of f of x. You don't care about the value, just what's going to be the sign of f of x. So it's easiest when we take a look at the factored form of this. So x minus 4 over x minus 4 times x plus 2. And so you can either look at it factored out like this, or you could really cross off those x minus 4s, okay? Because the graph is going to look the exact same as just 1 over x plus 2. All right, it's going to look the exact same except for that removable discontinuity. All right, so let's get going here. If I were to plug in negative 2.01, well, 1 is a positive number up top. Negative 2.01 plus 2 is negative 0.01. So we get a positive divided by a negative, which of course is a negative, telling us that as x approaches negative 2 from the left, we're going to negative infinity. As x approaches negative 2 from the right, I'll plug in negative 1.99. You plug that in. 1 is a positive number. Negative 1.99 plus 2 is also positive, telling me, well, positive divided by a positive is positive, so I get positive infinity. Now, the removable discontinuity is a little bit different. We're just going to plug that straight in here. Okay, plug it straight in. The reason we couldn't do it with negative 2 is because we would get a 0 in the denominator. With 4, we could plug that right in. You plug in 4, well, 1 over 4 plus 2, that gives us 1/6. So that's the y value of that whole that we're looking for. And then the last ones we're looking at are as x approaches infinity, and I forgot to put the negative here, as x approaches negative infinity. That's what I'm looking for. Well, for both of these, because I have a horizontal asymptote, I know 1, right, I approximated this as x over x squared, which is the same thing as 1 over x. If you plug in infinity, it's going to 0. You plug in negative infinity, you could say, oh, it's going to negative 0. Well, that's just 0. All right, now it's just a matter of let's take all this stuff and let's put it together on a graph. All right, so putting it together on the graph. Here we go. So we've got our coordinate plane. Let's start off. We've got our infinite discontinuity at x equals negative 2. And hopefully you've kind of been following along and you've written some of this stuff down. Okay, infinite discontinuity at x equals negative 2. All right, let's see. We have a y-intercept at 1/2. So I'll say that this is 1 here. There's my 1/2. I've got a horizontal asymptote at y equals 0. So here's my horizontal asymptote. It's just the x-axis. All right, as I approach negative 2 from the left, I'm going down to negative infinity. And then as I go to negative infinity, it curves and goes that way. All right, that's not a great curve. It really should be more curved. All right, and then as I approach negative 2 from the right side, I'm going up to positive infinity. And then as I go to positive infinity, my function will slowly approach 0. So yeah, that's a lot of work to come up with this graph. The only other thing that we're missing, let's just graph our hole. 1, 2, 3, 4. Here's my hole right here. We'll say that's the point 4, 1/6. All right, so there is the sketch of my rational function. All right, we're going to show just one more example to help you guys out. If you want to skip it, that's fine, but I think it really could help. It'll show some different ideas because not every problem is going to be the same as this one. All right, so in this next one, we can't really factor the numerator, so we're just going to kind of stick with just factoring the denominator for now as x minus 4, x plus 3. That tells me that I've got 2 vertical asymptotes because I can't cancel them out with anything in the numerator. Okay, vertical asymptotes are going to occur at x equals 4 and x equals negative 3. Then for my horizontal asymptote, same thing. I'm taking, as x goes to positive or negative infinity, I could approximate my f of x as x cubed over x squared. And so it's really just going to approximate the function as just x. All right, it's going to be really similar to just x. Well, if I plug in infinity, it's just going to go to infinity. If I plug in negative infinity, it'll just go to negative infinity. So there's no horizontal asymptote in this case. All right, we do not have a horizontal asymptote. We're going to see how that affects our end behavior in a second. All right, let's find the intercepts now. So for my x-intercepts, I'm just checking when is that equal to 0. So when is the numerator equal to 0? Okay, and I plug in x cubed minus 8 needs to be equal to 0. Well, that tells me x cubed has to be 8. Well, hopefully we know the cubed root of 8 is just 2. So we got our x-intercept of 2. Let's just make sure that doesn't make the denominator 0. Let's see, 4 minus 2 minus 12. No, we're good. So my x-intercept is x equals 2. For my y-intercept, I plug in 0. So x-intercept is when f of x equals 0. Y-intercept when x equals 0. I get negative 8 over negative 12. That's 8/12, which is 2/3. So there's my y-intercept. All right, now the limits. We're going to have we got a lot of limits to do for this one just because we have 2 vertical asymptotes. So our first one occurs at x equals negative 3. So we'll approach that from the left. And we'll approach that from the right as x approaches negative 3 from the right. Then we have one at 4. We'll approach that from the left. And we'll approach that from the right. Limit of f of x as x approaches 4 from the right. And then our end behavior. What's happening as x goes to infinity? What's happening as x goes to negative infinity? All right, this is going to be some exciting stuff. So negative 3 from the left. And remember, this is probably easier when we have it in factored form. So I'm just going to write it out so I can kind of help myself here. All right, let's plug in negative 3.01. So I go f of negative 3.01 just to the left. I plug that in the numerator. Well, negative cubed is negative. Minus 8 has to be negative. Negative 3 minus 4 is negative. Negative 3.01 plus 3 is also negative. So I get a negative because I have 3 negatives. Okay, if you have an odd number of negatives, it makes the whole function negative. So that's negative infinity. Negative 3 from the right now. So I'll go negative 2.99. Again, a negative cubed is negative, minus 8 is negative, minus 4 would give me a negative, plus 3 gives me a positive. I have 2 negatives, which overall is a positive, so this is going to positive infinity. 4 from the left, I'll go f of 3.99. That would give me a positive, right? 3.99 cubed, that's about 4 cubed, which is 64, so yeah, 64 minus 8 is going to be positive. Negative and positive. I have 1 negative, which makes the whole thing negative, so that's negative infinity. All right, down here, f of 4.01. Let's see, that gives me a positive in the numerator. Positive when I subtract 4. And positive, they're all positive, which gives me a positive. We're almost done, don't worry. All right, now these two. These are the most important two because these are a little bit different. So remember, we said as x goes to positive or negative infinity, we could approximate f of x as x cubed over x squared, which we said is the same thing as just x. Well, imagine you're plugging infinity into x. What are you going to get out? Just infinity, right? You plug in infinity, you're going to get it out. You plug in negative infinity, you're going to get that out too. All right, so we're going to notice that this rational function is going to have kind of some interesting end behavior here. So let's sketch this out to finish it out. And again, I hope you took down the properties of this because I cannot be scrolling back through. So let's see, negative 3, we've got a vertical asymptote. X equals 4, we've got a vertical asymptote. I'll put my intercepts next. Let's see, our x-intercept is 2. Our y-intercept was 2/3. I'll just put that there, kind of like a little approximation. All right, now let's see. As x approaches negative 3 from the left, we were going down to negative infinity. And then as we went to negative infinity, we also were going to negative infinity. So we're going to kind of curve back that way, and we're going to go back in that direction slanted. Okay, it's called a slant asymptote. We're not going to go too deep into it, but as we go back towards negative infinity, it should be slanted and down. That is a slant asymptote whenever you can approximate it as x, or if you could approximate it as like a negative x. Again, it's going to have a slant asymptote, because think of the graph of y equals x. That's a slanted line. All right, as we approach -3 from the right, we're going up to positive infinity. We'll curve through these two. As x approaches 4 from the left, we go to negative infinity. As we approach 4 from the right, we go to positive infinity. And then we are going to slant up to the right. And that is our final answer for the graph. If you want to check out Desmos to take a look at it, make sure we did it right, you could definitely do that. I think it's pretty cool that we can take this and have a pretty good idea of what the graph of that would look like. So nice work, and best of luck to you on